and welcome to the Engine Performance Expo. My name is Joe Castello, joined by Lake Speed Jr. and Andy Rottler as we get started on a journey for the next couple of days. We're going to learn about honing, building, everything high performance. This is our second edition of the Engine Performance Expo, and Lake, judging by what we did last time, I'm super excited. We've got nearly every big engine building personality right here in the house.
Oh my gosh, Joe. We got Ford, Chevy, Dodge in the house today. I mean, we are only 7 miles from Bristol Motor Speedway. Thunder Valley race this weekend. Yeah, we're back, and this is going to be better than ever before.
Yes, NHRA Thunder Valley Nationals in town, and that means all the bigs are here. And of course, speaking of big, we've got Andy Rottler making it all possible, talking about machining high-performance engines. I think you know a little something about that, Andy.
Well, I've been in the machining part of the business for a long time. My expertise is machining, putting finishes on engines and all. I'm not an engine builder myself. It's our expertise is doing the machine work for the engine builders, and we love doing it. I've been involved in it for 30-40 years anyway, and we enjoy it an awful lot, and we really appreciate everybody that has gotten involved in this program, and hopefully it benefits everybody out in the rest of the world. There's a lot to learn, and these people know what they're doing.
Yeah, that is the case. And for those that are fans of motorsports, there's something for you too. We got some big personalities going to be here over a couple of days. Tim Wilkerson, of course, George Bryce going to be here, Warren Johnson, John Kazi. These are guys that are entertaining outside of the car and also inside of the race car or the engine shop.
Well, they've forgotten more about engines than I'll ever know, and that's the key, is that these guys are here to share with you what they've learned. You know, like Andy was saying, their expertise isn't building engines, it's about getting the finishes and the geometry, because that's the real key to making engine performance. The other day we were looking at a conference, the Production Engine Rebuilders Association conference, and they had one of the new Ford EcoBoost engines there. It's got half the displacement of a 289 Ford, but it makes the same horsepower and torque as a 289 Ford. So think about that. It's crazy.
Yeah.
So the technology's come so far, and the way you reach that higher level of technology is having the correct surface finish, the correct geometry. And these are the experts, the guys who've been there, done that, and that's what the whole ethos of the Engine Performance Expo is to share that with you.
Share the information so you don't have to invent it yourself. Hopefully there's a lot of people out there that are using this information and even advancing beyond it. It's a non-stop process to continuously improve what we're doing.
And I also want to say welcome to the folks on NHRA.TV as well. Those of you that are members of NHRA.TV getting a little special bonus here with the Engine Performance Expo. And all of this will live forever on the internet. So it is a resource. If you see something here and you're like, oh my goodness, what did he say? That was incredible. You definitely should run for a pad and write it down or put it in your phone. But it will be up on the internet for you to reference over and over again. And as I mentioned, this is the second one we have done. And over the course of the year, since the first one, it has been nonstop feedback, people going back, finding moments.
The John Kazi video from the first one, I mean, we brought back John, right? John's going to be one of the, we should go ahead and John's going to be here live here in about an hour or so. It was the most watched segment. I've been into shops here recently, and the guys are like, oh, I've got my John Kazi Scotch-Brite wheel, because they watched that video. It's so helpful. So, you know, that's part of the thing that really this is all about. The people who've been around this for a long time have probably heard of what was called the Advanced Engine Technology Conference, or AETC. And that's kind of really what we're modeling this after. And of course, it was thankful to Andy and Rottler, their support, to be able to make this happen. I should probably thank Matt Hartford as well, because Matt and the guys at Total Seal helped make this possible. You know, so it's a collaborative effort between Rottler and Total Seal and a cast of thousands that have made this possible. But to bring what AETC was, because it doesn't exist anymore, and make it available to everybody on demand. Because there were some moments, like the John Kazi thing in the first expo, that happened at AETC. In fact, he gave that same talk at AETC 10 years ago. but no one knew about it. If
Yeah.
you weren't in the room, it didn't happen. Now, with this format, it happens, and you can still watch it. You could have watched it yesterday to figure it out.
Yes.
And you could watch it a year from now and figure it out. So that's really the kind of the ethos to me of why the Engine Performance Expo is so important, is to get that knowledge, that information,
Yes.
that guide path, if you will, from these legends and solidify it so that it's here for generations to come. So you don't have to start at the bottom of the mountain. You can start halfway up and make that journey to the top. And this is what it's all about.
Yes.
You know?
Sharing tricks of the trade, information. You work a lifetime to figure out the best way to do something, and what happens to that information. It just goes away when you pass on. No way. It needs to be transferred, and that's how the whole civilization moves forward. And when it's something as simple as John Kazi made a tool, or he teaches us to get our headers coded, otherwise we're in big trouble.
Oh yeah, we're going to talk about that today, by the way.
have-
I can't wait to get John on here and have that conversation.
That
again.
one is the one that stuck with me from the first one. But we got plenty more to come. In fact, an entire engine is going to be built.
Right, so that's kind of one of the neat parts about this, is that, let's say, last time we went through the process of building an engine, but it wasn't the same engine. It was this, that, the other thing. This time, in amongst the other features of having some celebrity guests to talk and to do some advanced technology features and things, like we got one coming tomorrow with Tim Wilkerson's guy, Jeff Jacobs, how he welds aluminum blocks to fix them. Because you know those top fuel cars, they tend to kind of blow up sometimes.
Yeah, things break.
Yeah, things break. So they got to fix them. So he shows us how to do that. So in amongst those kind of segments, we're actually going to build what we hope will be a 1,000 horsepower-ish LS engine. And we're doing that from pretty much off-the-shelf parts.
That is incredible.
Now, here's the cool part, though. That's step one. Because one of the things is every engine tells you a story. So putting the engine together is one thing. When you take that engine apart, there's a whole other story you get to learn. So come back in January, we're going to have the complete engine running. So this is 2 segments. There's 2 days now in October, 2 more days in January, also the 13th and 14th, by the way. So we're going to have 2 days now, 2 days in January. Over that whole process, we're going to build that engine, we're going to dyno that engine, and then come around next year, we're going to be able to have that disassembly of the engine. And hey, read those bearings. Did we get the bearing clearance right? Did we have the warning system right? We don't know. It's the first time we're ever building this engine. I mean, there's people of experience, but you don't know until you do it. And then we're going to be able to have that deconstruction. So this is a multi-phase process where we're going to bring you along with a ride, and we're going to show you the exact things we learn as we learn them. So yeah, I can't tell you how excited I am about this, man. This is going to be the coolest thing I've ever been a part of, and we're doing it in front of God and everybody, so hey,
Exactly.
no hiding.
And in case you're wondering, I've put in my application to be the one that beats on the engine, but they're still reviewing that. Andy, you work with so many different people in this industry. To see this collection come together, we got Warren Johnson in the house. He's going to be on later. We got Roy Johnson in the house. So we kind of got a Chevy perspective. We got a Mopar perspective. We got John Kazi, which is a Ford perspective, of course. We got big drag racing in town this week. It's got to be great for you to be able to connect with all of these different people all in one place.
Yeah, having the best in the world, it's fantastic, and I hope everybody enjoys it, learns a lot from it, and looking forward to continuing the whole process.
So Lake, talking about the engine build that we have been working on, that is going to be our first bit. You and Ben Strader got together, and everybody knows Ben is an ace and deep thinker, to say the least, EFI University. You're going to start us off. Give us a little preview of what we're going to see.
You know, just like our buddy Keith Jones always says, making your first call, not your last call. So what we did was, hey, we're building an engine. Let's go to Ben. Let's figure out what we need to build, right? If the idea is, hey, we want to do a boosted, pro-charged 1,000 horsepower LS engine, well, what should we do for bore size? What should we do for stroke? I mean, all these kind of things. What does it take to make 1,000 horsepower? So Ben, being the wizard that he is, pulled out his calculator, sat down and does the math, and kind of takes us through that whole process of thinking through how you plan your build so that you end up where you want to end.
Excellent.
Wow.
Andy, thank you so much. We're going to have you back later on. We're about to get started. Engine Performance Expo, Ben Strader, Lake Speed, the engine. Here we go. Let's check it out.
Hey there, Engine Performance Expo. I'm Lake Speed Jr. I'm my buddy.
I'm Ben Strader.
Here at EFI University. And so here we are, we're kicking off the brand new 2021 second edition Engine Performance Expo here in the fall, although we're actually in Lake Havasu right now
In the summer.
Yeah, it's hot outside. Anyway.
It takes a long time for us to get ready for you guys to do this.
And we have a whole lot of work ahead of us, trust us. This
yeah.
is the easy part right here.
Yep.
So anyway, we're going to be talking about the featured engine build. So now last year we went through all the machining steps and process like that, but we didn't really build an engine.
Yeah, it was a little different concept, right? Like last year was why would you do this and how would you do that? But at the end of it, it was a lot of conversation. And this year we're going to put our money where our mouth is and actually make something.
Yeah, and run the dyno.
Oh man.
Hope it doesn't blow up.
But I think what's going to be interesting about this year is you guys are going to follow along the entire process. Now, this is not just a, hey, we're going to build an engine process. We're going to start at the beginning and talk about the thought that went into the design, the component selections, the specifications, and then go step by step along the way as the various jobs get done from the machine work and the assembly, and then we'll bring it here and, get all that Holley EFI stuff on there, get the Pro Charger, see what happens.
Tune it up a little bit.
Yeah, exactly. What did Warren say last year? You can't tune
it up if you blew
it up. So that's going to be my problem, to try not to blow the darn thing up. But I think we'll be all right, and I think you guys will be excited with what we have for a package this year. And so let's talk a little bit about the package and what you think it's going to look like.
Yeah, so here's the interesting thing. We're talking about building an engine, yet we're in front of a whiteboard. There's no blocks here, no heads here. There's nothing, even tools to measure anything with.
That's right.
So why are we in front of a whiteboard if we're talking about building an engine, not at a lathe or something making parts?
Standing at the machine. Well, I think one of the common errors that engine builders tend to make when they start on a project is a lot of times we'll just look around and go, well, I got this thing laying around, and I got that crank and this block, and we'll just throw this together, and you end up with some combination that maybe works okay, or maybe it didn't quite meet your expectations. And so the way that we tend to do it here at EFI University, like, we teach that competition engine development course. We start with a blank sheet and go, okay, let's talk about what your goals are. What are the criteria that we have to meet? So we all know the big one, right? So how much horsepower do we want?
Oh, yeah.
That's an easy one. Everybody wants all of it, right? But then we look at, okay, well, what are the restraints, right? Do we have rules, restrictions?
Exactly.
Do we have budgetary, constraints? And as we found out, even just trying to put this package together, what about supply chain issues and timelines?
Yeah, exactly. Yeah. This is 2021, and you're going to be watching this in 2021, so you already know you can't find normal things.
Yeah, no, it's been a real challenge this year. Even with all the great manufacturers we have on board, they just can't keep up with their own, supply chains and demands and stuff. So we actually started out with the idea that let's do it just the way we do in the class. Let's start with a competition race type engine. This thing will do 10,000 RPM, and it'll just blow the planet up kind of thing.
Oh yeah, obviously we have a common friend.
Sure.
Kevin Studecker, and it's one of the kind of thoughts on this thing came out of last year. It's like, wow, build a really cool drag week engine.
Yep.
Because that's one cool thing about drag week is you don't have the kind of rules restrictions that you would say having like my background in NASCAR or some of the stuff you do in drag racing, where there are very specific, tight, confined rules, which can be fun if you're a John Cosby of the world, right?
Yeah.
But when you don't have a lot of rules, that freedom to do whatever can
really
be a problem.
Yeah,
too,
so it's a catch-22 because the good news is we literally could do anything we want to do.
Right.
But now the bad news is we could do anything we want to do. So we admittedly got a little carried away at first.
Oh yeah, I wanted to go 10,000 RPM, make 2,000 horsepower.
Yeah,
why not?
Which is not out of the realm of possibility. But generally, when we start with a project like that, we start with a clean sheet and the whiteboard, and we look at what are those factors. So some of the roadblocks we ran into were time constraint. Can we get parts in time? Can we get the right parts that we need? And so I think what we decided is to take a step back and really rely on the same basic formula that's always gotten us through to now, which was we started at the chalkboard and started mapping out what would an engine like that look like. And at one point, we all sat down and just took a deep breath and kind of looked at each other and said,
yeah, no.
We may not be able to get there from here with what we have available.
Not in one step.
Correct. So what we decided to do this year was start the same way, but change the goal, right? Instead of 2,000 horsepower, 10,000 RPM, let's build a more realistic package. And so what we decided to do is let's take a combination of parts that you could buy, an average guy with average skills could buy off the shelf, pay attention to the details, the measurements, the machine work, get all of it right, and how good could it be? So you're going to follow along in this journey with us from the initial concept. We're going to work through the math on the chalkboard, see how we ended up with these design dimensions, and why we ended up with those parts, right? Some of it's driven by cost, some of it's driven by parts availability, some of it's driven by compatibility. Well, look, everybody wants to do 10,000 RPM, but not everybody wants to put 937 lifter bushings in their block for a cost of $4,000. And so then you go, okay, if you're not going to do that, then you can't do this. And if you don't do this, then you can't do that over there. And that's the way we start. Rather than a box of parts that got donated by 20 different companies that are all genuinely of good,
great parts.
Yeah.
But you have this Frankenstein, no offense to the cylinder head guys, right? Combination of an engine that's got all these parts that are mismatched.
Yeah.
And then it doesn't do what you want it to do. And you fight gremlins and chase things because it wasn't thought out through.
The end result becomes disappointing because we didn't start with the right foundation, right? So what we're going to do is walk through, how do I determine things like what would I want for a bore and a stroke? How would I determine how much cylinder head this thing really needs? How would I determine what the camshaft needs to look like, and how is it that there's always those guys you can call? We all know King Kazi, right? You can go ahead for just about anything. He's going to have the answer, but how did they get there without 50 years of experience like those guys have? If you're out there starting out, you've been in the industry 5 years, 8 years, 10 years, and you're going, man, I feel like I'm never going to get there. Part of the reason is because nobody ever seems to want to start with the blank chalkboard and the calculator and the pen and the pencil. But I think what the value of learning how to do that segment is that you shortcut that, maybe 25 of those 50 years of trial and error.
Oh, yeah.
You could skip over all that, hey, I bought the wrong part, hey, I got the wrong system. And once we understand that the engine is really, the total package is a series of interconnected, interdependent events, and that if I change one little thing over here, it affects 10 other things all across the board.
Exactly.
When we begin to realize that if we start with the end goal in mind and we map it all out from step one, we'll end up with a pretty good package. And I think this year's package is going to reflect that. You guys are going to see by the time we get done, wow, I could build that same exact thing. It's not going to be some crazy exotic, over-the-top thing. But we want to get there over the next couple of years.
Right.
So what we want to do...
Because we still wanted to have fun, right?
Oh, absolutely.
Oh, we're going to have fun.
Yeah, there was a moment when Lake went, man, I don't know, that's going to be so boring to build an engine like that. And it was like, no, let's do that, because what you guys might find interesting is how do we get from the normal average type of performance engine that everybody is capable of building.
Right. The off-the-shelf parts engine.
Yeah. So how do I get from that to that really next level, one-off, custom engine? And I think this would be a great way to segue to that next year.
Oh, yeah. The comparison. Yeah. That's one cool thing about this. By having this be a 2-year project, not a 1-year project, what's really cool is we're going to be able to go through, here's the build. Here's how you pay attention to all the blueprinting, the kind of the details.
What should I measure? How do I measure it?
We can go through all that and get it and run it and show what it is. Then we have the ability to take the engine apart and do the reverse blueprinting. So already one thing that's going to happen next year is there's going to be another video here with you tearing the engine apart, doing that inspection, that reverse blueprinting. Then we can do the compare and contrast of, okay, we're going to turn 10,000 RPM. Let's look at these lifters we have. Now let's look at the lifters we need.
Yeah, let's look at how much camshaft we have. Let's look at the weight of the valves. Let's look at the valve springs. But
the piston rings.
The piston rings.
The piston rings are going to be different.
I would imagine.
In a 10,000 RPM engine versus one that's a 7,000 RPM engine. And you may think, why? But
We're going
to show you why.
Yeah,
So
I would imagine there's even an opportunity to do an oil sample in there and see how.
Oh yeah, we're going to do all kinds of fun stuff.
One of the most exciting things about doing real engine development work is the aftermath. It's that reverse blueprinting. You know, everybody's pretty familiar with, I blueprinted an engine, I measured it, I machined it, I spec'd it out. Maybe you even took records, for God's sake, right?
Oh, yeah.
What we're going to do is we're going to take the engine apart slowly, one piece at a time, investigate it, measure it, look at it under the microscope, record it. So we're going to end up with 2 documents, right?
Yep.
Our original blueprint document, and then our here's what changed when we ran the engine document.
Exactly. And that's key, because the engine's going to tell us a whole bunch about if it was happy or not.
Yeah, we're going to be looking at bearings, piston rings. We're going to look at
free gap. I mean, free gap. There's a whole video that Keith Jones had done about that.
Yep.
Free gap's a huge thing to find.
Yep.
Is my tune-up happy?
Yeah, absolutely. What about cylinder bore finishes, right?
Yes.
So things that can change while the engine's running, things that can wear out or get cracked or broken or used up. That's what we're going to show you how to look for when you take the engine apart. I think that's a huge mistake that guys make. They take their rattle gun and they zip the engine apart. They throw all the things in the cleaning bin and they go over to the tank and somebody washes the parts for them and then we put it back together. Well, I think you miss a big opportunity.
Oh, it's huge
that way. So we're going to go through that process after this year. So hopefully we have a scheduled disassembly of the engine, not an unscheduled disassembly.
No, we hope it's all under control. It's not panic mode.
So that's what we call blowing up an engine around here. We call it a rapid unscheduled disassembly of the engine. So we're going to try not to do that for you, but it's going to be a pretty cool path that you'll get to travel with us as we go along to create, design, develop, build this engine. Then we'll take it apart and disassemble it, inspect it. Then we're going to start looking at how do we get this from a, what I would like to call a semi-custom shelf part type engine to a really one-off custom project for next year. And so what that does, not only does it buy us some time to get the supply chain and get the things going, but it shows you guys a little bit of the path and the sort of process that it takes to do that.
Well, yeah, again, because then everybody knows, okay, well, hey, this keyway lifter is better, supposedly, than this OEM lifter, right?
Right.
So this is going to give us a real chance to go to the Spintron and actually show what's that difference quantifiably, not just in the price tag, but what does it actually do in the engine performance. And then hopefully the real cool thing is you got the dyno, so we can find out what power does this thing make, and then we can find out what it does when we make the changes.
Yeah. So it's pretty exciting. I'm glad that I got invited.
It's the torque ratio, right?
It is the torque ratio.
We're going to find about that.
We're going to talk a little about that when we do our engine design project. But I'm pretty excited that for the second year in a row, I got invited back to be a part of this, Engine Performance Expo. And I hope that it will turn out to be even more exciting than the one last year.
I think so. Well, we learned a lot the first year, right?
Sure.
You don't know what you don't know, and that's what always scares you. Right. But then you do it the first time, you learn some things, you're like, okay, wait, we've got the feedback, we know what we want, people want it, and we know what to do better. So that's what we're trying to do. So here we are. We've all that to kind of be the preamble, if you will, to this whole segment in the show. So this is what we're going to be doing with this project, right? So the idea of the project is this drag week type engine. So Ben, tell them a little bit about what the specifics of this engine that we are going to do.
So drag week is a challenge because you want an engine that makes a ton of power, obviously, because it is drag racing. But there's a lot of things that we can't do in a drag week engine that we would do on a pure drag race engine that gets trailered and treated nicely.
Because it has to drive back and forth.
You actually got to make a 1,000-mile drive along the way. I was lucky enough to do drag week on 2018 with Kevin and our mutual friend.
Hollywood and Wagon of Doom. There you go, buddy. Calling you out.
Wagon of Doom, yeah. And we didn't break it. We finished. We actually finished second in our class, which was pretty good for a tubby old station wagon. And so I learned a lot from doing that too. There were things that I hadn't even considered as an engine builder, strategies as a tuner, right? So sometimes you just got to go and experience that before you go, next time I do this, I'm gonna do that differently or watch that. But at the end of the day, one of the key things was we have to have reliability. Right. So that means structurally the engine has to be able to survive at a relatively high power level, but it also has to be able to drive and drone along the freeway for hours on end going 65, 70 miles an hour too. So what we started out with is a LSX aftermarket, basically bow tie block.
Yeah, the Dart iron block.
Oh, we're doing the Dart one. Sorry.
Yes, yeah.
So I knew we had been talking about which one we're going to use. We either have the Dart LS Next.
Yes, LS Next Dart iron block.
Okay, so we knew it was going to be iron. We just didn't know which one we were going to go to. But at the end of the day, what we wanted was strength, and we wanted that priority main oiling that we get in the aftermarket block. Yeah. So the oil system in that, even though it's an LS style block, is dramatically different from
big time factory. Oh, yes.
LS, where the factory ones tend to oil all the valve train stuff first, and then whatever's left over goes to the main bearings and rod bearings and all that. So that's a huge advantage to that block. The other
it's iron versus some of the aluminum.
True. Yeah.
Production blocks.
Yeah. And we can go to a larger bore than we could if we say I wanted an iron factory LS block. I'd be stuck with like a LQ9 6-liter style. Then we get limited on bore size, and bore size is something that we really want. And the aftermarket block allows us to do that. We can actually get a lot larger bore in that block than what we're going to use for this project. But there are some structural considerations, like the bore center of the block being 4.4 inches limits what we're going to need left over for meat in the block. We start making boost.
Right.
So that becomes our limitation for bore size.
Exactly.
Right. We didn't want some exotic stroke length in the thing. We wanted to use a factory stock 3.622 stroke. So effectively, the engine size set itself for us, right? So
exactly, yeah.
So that's a pretty common LS configuration, kind of a 4.125 bore stock stroke. You end up with 387, 388, somewhere in that neighborhood. Very common configuration. So we thought that was relatable. We wanted to stay with a stock lifter bore size, which is the 842 lifter. That really limits how much RPM we can do on a regular basis. I'm of the opinion, after having broken a lot of lifter stuff, that at least in the
you have that electronic braking tool back there, right?
Yeah, I have that engine destroyer back there. And I have figured out that, at least in my opinion, for the LS engines, 8,500 RPM is really the absolute ceiling upper limit for RPM, at least on any kind of regular basis for that stock lifter.
Got it.
And we'll get into why when we get to that point. We'll look at the rollers and the axles and how much meat you get there. But for the amount of lift and how fast we need to actuate the valves, how much spring pressure you get, it just doesn't lend itself well to being more of an endurance type of.
And back to that durability. That was one reason why we wanted to do the stock stroke.
That's right.
Is that, yes, that block, because of the spread pan rails, you could run over a 4-inch stroke in that engine.
Yeah.
But now you're going to be making that piston really unhappy.
That's right.
Because you're going to be making the piston want to rock.
Especially at the bottom, right? It comes out the bottom of the cylinder bore. And that particular block even has a longer cylinder length to help with that.
Yes, it does.
But it hurts the piston skirts. It upsets the rings. And man, Lake does not like it when the rings are upset.
No. Ring seal is everything.
That's right.
If you're watching this and you happen to be a listener to the Hidden Horsepower podcast, you will know that pretty much every top engine guy that's been on that show, they talk about the engine being a pump, and you've got to seal it up. And
a lot of people forget
we're ring seal guys, we're piston ring guys, but as anybody knows, ring seal is soup. It's not steak.
Yeah,
it's not just the ring. It's the whole concept, and that you can have the right oil, you can have the right ring, the right cylinder finish, the right piston, but if it's rocked over like this, it can't seal up.
Yeah, it's at an angle. So a lot of people think about that at the top of the bore, but not everybody thinks about it at the bottom of the bore, and that matters too. So
oil consumption.
Yeah, absolutely.
It's a big thing. So you can put a 4.125 stroke in some of these things.
Oh yeah, easily.
But
some guys are putting bigger than that.
You're going to get oil consumption.
So there's trade-offs, right?
Yeah,
we know there's things that we can do, but remember, the goal is we got to drive this thing 1,000 miles, making hits at the drag race at wide open throttle and high RPM every day.
Right.
So
we don't want oil in the combustion chamber.
That's right. We want
oil
to keep this
is
thing
low octane.
Yeah, absolutely.
We've seen that here, right?
Trust me.
Oil you don't want in the combustion chamber, especially if you're making boost.
Boy, it's going to get harder. The more cylinder pressure you create, the more power you're making, the cleaner that combustion chamber needs to be, or you're going to run into problems. And
so that's one thing about this.
Yeah.
I'm a boost newbie. I'm from a completely naturally aspirated background. From my very first 2-cycle go-kart when I was 4, all the way through my dad's career, even me and Dad going back into vintage go-kart racing, I've never messed with anything
you're missing
that had boost. So this is a whole new territory for me.
I feel like I'm known for all of my NA work, but the reality is I've done a lot of turbos and supercharged, and
you mean
it's pretty addictive.
You can't see that, but there's a whole bunch of turbos over here.
Yeah, we've done the turbo thing up one side and down the other. Superchargers, it's pretty addictive. Boost is pretty awesome, and we're gonna
excited.
that. So this engine's going to be cool. It's going to represent, an LS3 style engine. So we're going to use an LS3 head with CNC ports that are done by Chris Straub, right?
Yep.
I think he's doing the camshaft as well for us.
Yes, he is.
So we'll have a camshaft, valve spring package, all that sort of helped been developed by Straub Technologies.
Yep.
With their cylinder head package.
Correct.
Holly's going to supply us with the top end of the engine, so that's going to be intake manifold, EFI system, all that. It'll be pro-charged.
Yep, pro-charged.
So we're going to have a pro-charged LS3 Dart SHP 388-inch combination. Man, I'm not going to make any predictions on what it's going to make, but it's going to make a ton. I can pretty much guarantee you that.
I can't wait. The cool thing is, it's like I said, it's all shelf parts,
Stuff that you can buy.
The push rods, the springs. Mark Campbell, the guys at Comp Cams, giving us the shaft rocker mount system.
Yeah, that BSR system's crazy cool.
Super cool. So, but these are all this catalog part pieces you can buy. So it's going to be kind of cool to see what kind of power we can make.
What can be done with it.
With that.
Yeah.
Then next year.
Yeah, then it's going to get fun.
Yeah, you're real crazy. So.
Yeah, so we'll have to change everything about the engine then, right? So that means we'll probably need longer valves because we need more lift. We need a bigger camshaft. That means we need bigger lifters. That means we need more valve spring in the thing. And we'll have to spintron it to make sure all that's going to work.
Yes.
If we're going to do more RPM, then those valves are going to be kind of heavy, so we're going to probably want a different valve material.
I'm glad you mentioned that, because you mentioned the valves. It's not just changing the valve length, but valve material is going to change. This is not going to be a steel valve.
No, we'll end up with a titanium valve in it. Yeah. So, but that's for down the road, right? I think the fun of this year's event is going to be following the process. How did we start? Knowing where we're eventually going to go with it. Where are the places that we can't cut corners? I hate to use the word cut corners, but where are the places that we can't compromise?
You don't want to paint yourself into a corner, right?
Correct.
If we chunk a piece of metal off the engine now,
right,
that we actually need later because of what we're going to be doing, we've already.
It's easy to take it off the engine. It's really hard to put it back on.
Yeah,
So we want to be careful about that in the planning process, so that we leave room for what we want to do.
We don't have scope to do what we need to do as we go forward.
Yep.
So talk a little bit about what are the challenges from the math side. Right? That's one of the things I heard recently on a podcast. A guy was saying that for him, growing up poor, math was a way for him to actualize things before being able to make them. He didn't have the money to go try things.
Well, he didn't have the luxury of being wrong.
No. So for him, it was doing the math. I could mathematically translate these ideas into something practical if I could work out the problems beforehand. So let's talk about the math a little bit for what we're trying to do.
Okay.
What are the big things we need to be looking at? Like somebody else is watching this saying, man, I want to do this. What math do they need to begin to be thinking about in order to actualize their idea with lower risk of having, what'd you call that? Rapid, unscheduled.
Yeah, disassembly. You don't want that. So I'll tell you how we do it in class. Normally what we do is let's solve the biggest problem first, which is what is the goal for how much power you want to make?
Okay.
We're all familiar with the term the engine's an air pump.
Yep.
Right? So what I usually start with is if you tell me how much power you want to get, I'm going to say, well, I can tell you how much airflow it's going to take you to make that much power.
Right.
Now, how you get that airflow is up to you. You want to do a 10,000 RPM naturally aspirated thing, or you want to do a 6,000 RPM thing that has boost to help you get there. At the end of the day, we got to get to the same amount of airflow one way or another.
Right.
So that becomes one of the first factors. Well, is this planned to be NA, or is it planned to have boost? So then we go, okay, what's the engine displacement next, right? Because that determines the size of my air pump. If you have a really big air pump, you don't have to turn it very fast, and you don't have to add very much boost before you get to the amount of air you need
to make power. Right.
So until we start with how much power do you want to make, it's hard to go forward from there. Now, a lot of times the conversation starts differently. Let's say you have a performance shop, right? Guy walks in the door and says, I want you to build me this engine. I got these parts already. I got this engine. I want to go through it and freshen it up, overhaul it. I want it to make, 900 horsepower. Well, a lot of times what we'll do is you'll use this math to determine if that's even possible, right? Because we might be just wasting our time if we don't know how to do that. So we start with how much power do you want to make? That tells us no matter what, how much airflow we need. So what we got to get to is how are we going to get that much airflow? And so then where I typically go from there is it boost or NA? And what size engine do you want, right? So engine size is widely contestable and arguable and sometimes restricted if you have class rules or you have budgetary, right? So in our case, we know it's going to be a supercharged engine, right? Which means I know that I'm going to need a bunch of cylinder wall bore so that it's stiff enough to withstand that cylinder pressure. That means big bore stuff is out. I can't be doing a 4200 or a 4210 cylinder bore like we might do.
You could with that block, right?
I can with that block, yeah, absolutely. But
we're not going to go anywhere near that because we got to make big boost.
If this was NA, then I would say, okay, let's do that. But because we want boost, that's off limits, all right? So there, we ran into our first roadblock, our first limitation. So we got to figure out what is the least amount of cylinder bore that I can live with and have left over, and that will basically subtract from my 400 bore center.
Right.
And we're going to end up with about a 4125 bore. It's no accident that the vast majority of LS high-performance engines that are boosted end up at 4125 bore. You know, if you do the math, you can figure out how much cylinder you got left over there. 4125 out of 4400, you know, whatever that is, 275 thou or something. Split that in half and divide it by, you know.
That's your wall thickness.
That's how thick your wall is, right? So we're kind of stuck with that limitation.
Yeah.
So
because if you have a Pro Charger, you're not going to run 6 pounds of boost.
Probably not.
It's like why? Why would you do that? It's like if you had a Cub car, why would you ride around in second gear?
That's exactly right.
Put it in gear, go.
After a little bit.
Exactly.
So once we have the bore size, then the rest of the displacement project is, well, what do you want for crankshaft, right? And because we wanted longer term reliability, we wanted good ring seal. We didn't want the piston coming out of the bottom of the engine. So we said, let's stick with a stock stroke. That's how we ended up at that 387, 388 inch profile. A different engine for a different application. Like let's say you said, well, I want to do pro charging, but I want to go to, 10,000 RPM. Can I keep this situation the same? Well, maybe you can, maybe you can't. We'll look at things like piston speed limitations and all that. The next thing we have to do...
stroke may have to be shorter.
It might, yeah, depending on what you got going on and what your goals are for that. You might not want that much stroke. The next thing we have to do then is look at, well, how much airflow would an engine like this have if I didn't do the boost? So what I want to know is, well, how much boost is it probably going to take to reach your goal? If your goal is to make, let's say, 1,000 horsepower, right? And I do all the math.
Because you can't build an LS engine with boost and not make 1,000 horsepower, right? Yeah, you're not a man if you can't do that.
That's exactly right. So what I typically do is I'll take my combination and say, what do I think it would make using math, right? If it didn't have any boost, right? So let's say my goal was 1,000, and I've worked out that I think the engine can make 600 all by itself. Well, that tells me how much boost I'm going to need then, because I got to make up that 400 horsepower in airflow with boost, right? So if I start out with a 600 cubic inch engine, I'm probably not going to need any boost to get to 1,000. But if you start out with a 200 cubic inch engine, well, you're going to need more boost, right? So it's an iterative process that we teach, and I'll be happy to go through it, on camera for you guys live if you want.
Yeah, let's do that.
Okay, cool.
All right, stay tuned.
All right, everybody. Well, we got to the point where I had to get out the most important tool in the shop, the calculator, and Lake got scared and took off on me. So I guess it's just going to be me and you. But what I wanted to do was walk you through just a real quick motion. I'm not going to do a full, training course on how we do this, but just give you the high points of how we ended up picking some of these parameters out. So the first thing we needed to pick, as we talked about, was, what was the goal? And so I just threw out some arbitrary number of 1,000 horsepower. Now, to be honest, that may or may not be what we end up with for the real goal for this project, but I wanted to use it as an example for you to see how we got there. But so that being the case, we know that we're probably going to be building a pro-charged engine, which means boost and supercharging. So that's going to limit the size of the engine that we can build. We talked already in the previous segment about how we're going to keep the stroke stock, which is 3.622. And so then we have to figure out what we want for a bore size. Now we're using the Dart LS Next block. And when you get the paperwork from Dart, they have a sheet that gives you all the specifications, minimums, maximums, that kind of stuff. One of the things that they list is maximum bore sizes. Now they recommend a maximum naturally aspirated bore size of 4.185 inches and a maximum bore size for boost or nitrous applications of 4.125. So that's because they have to have a minimum cylinder wall thickness here of somewhere between 100 to 110 thousandths per wall, right? Hey, Lake, I'm going to stop because I'm not sure that's recording. It keeps saying portrait over here.
It is.
All right.
Yeah, it does that. These things do weird like that. It changes back and forth.
Basically, if the red light's on, it's recording.
Yeah. It tries to be smart, and when you're still, it goes in one mode. When you move, it does the other.
Gotcha.
This thing over here, that's the reason why this camera sucks, is because it moves all over the place.
Gotcha. Okay.
It's awful.
Yeah.
When you move, When it moves, it refocuses, it changes the light.
You're all, yeah, that's fine. Do you want me to start all the way over, or you want to just
pick
there?
Right here.
Okay, I'll just pick up right here. So
yeah.
All right, so we're starting out with the Dart LS Next block, and when you get the block, they give you a piece of paper that shows you minimums, maximums, tolerances, that kind of stuff, torque values for the fasteners. One of the things that they'll say in there is if you have a forced induction or a nitrous type engine, they want a maximum bore size of 4.125 inches. If you're building a naturally aspirated engine, Dart recommends no larger than 4.185 inches. Now I can tell you from personal experience that some people have cheated that and pushed that out a little bit more, and that's certainly possible. But I think the only way you could safely do that is to sonic check the block and make sure that you have the required wall thickness that you're going to need. Because you start getting down there, naturally aspirated, minimum wall thickness needs to be 100 to 110 thousandths of an inch per cylinder wall. That's both sides, right? So at 100, that's already 200. And if you're a 4.4 bore center, that's 4/200 bores, the largest you could ever hope to get. Remember, that's already 15 thousandths bigger than Dart recommends. And I can tell you from personal experience that you're starting to get into no man's land, and you can have failures of the cylinders out there. So be careful when you're pushing that. But think about this. When you go to a nitrous or a forced induction boost engine, they want even more wall thickness, 135 to 150, right? So that's why in a boosted application for LSs, you commonly see a 4.125 bore. That 4.125 bore, if you think, is 4/400 bore center. Take away your 4.125 bore and you're left with 275. So divide that in half, because half of it's on this side, half of it's over here. You're down to 137.5, which is really getting on the skinny side there. So it's not an accident that you see so many 4.125 inch small block LS type engines for that reason. So realistically, that kind of dictated what we could have for a maximum bore size. And since we wanted a stock stroke, to calculate our displacement is simply the bore times the bore multiplied by 0.7854, which is really just pi divided by 4 since we're squaring over here. The stroke length times the number of cylinders, and we get 387 inches. Now, once we had that, we had to figure out, like, okay, well, how much power would you expect a regular 387-inch engine to make? Well, it comes down to RPM and compression ratio, and it boils down into something that a lot of engine development guys use called brake mean effective pressure, which is the average amount of work being done in the cylinder across your power stroke. A simplified way to think about that is what we call torque ratio. It's how many foot-pounds of torque does the engine make based on the size of the engine. So it's foot-pounds per cubic inch naturally aspirated before we add the boost, right? So as an example, because this is a drag weak engine and because it's going to have boost, we know that it's gasoline based. We could use gas, maybe even race gas, but it's not going to be methanol. So it's going to limit our compression ratio to probably somewhere in the neighborhood of 9 or 10 to 1 maximum. Now the amount of compression ratio we have will make a big impact on the engine's performance, but I'm going to say that for most road-going, high-performance, gasoline-based engines, you're probably not going to see more than about 1.4 foot-pounds for every cubic inch unless you work really hard on the engine. I'm talking about naturally aspirated, right? So for example, our engine's 387 cubic inches, so 387 times 1.4 means that I would expect 542 or somewhere around 540 foot-pounds of maximum torque. Now I got to figure out at what RPM I want that to happen at. Well, we chose to consider and focus on the reliability of this engine because it's got to drive for 1,000 miles and drag race. Look, we don't want to have to change valve springs at the end of every day. It's a wet sump engine, not a dry sump engine. We got to think about the component weights. We got to think about the fact that we're still using that 842 stock lifter. So even though we could get away with more RPM, and I really mean just get away with more RPM, I really felt like for this project that a 7,000 RPM upper end limit would give us the power we need with the reliability we're looking for. So that being said, if you look at enough dyno sheets, you would probably find a trend where a well-developed engine is usually going to make maybe 90% of its maximum torque by the time it gets to peak power. In other words, so we say, I'm going to make 542 maximum foot-pounds, and by the time I get to peak power up here at 7,000 RPM, I'm still going to be making 90% of that value. So that means if you look at enough dyno sheets, you notice that on average, most of the time your peak torque value happens at an RPM that's around 70 to 80% of the peak RPM value. So think about that. If I'm going to peak at 7,000 RPM for max power, then by the time I'm 25% less RPM for that, I'm going to be between 5,000 and 5,500 RPM for peak torque. Sounds pretty familiar if you've done a lot of LS engines, right? So we would expect 540 plus or minus a little foot-pounds of torque around 5,000 to 5,500 RPM. 10% less torque than that by the time I get to 7,000 RPM means I'll still be making about 485 to 490 foot-pounds by the time we get to 7,000. So we picked 488, and that would produce 650 horsepower. Not that far off from a lot of really high-end, well-developed 388 cubic inch LS3 engines with a good cylinder head, good manifold, good exhaust package. Remember, the engine's a system, and if it's fully well developed, it's not unreasonable at all to make that kind of power. The problem is that's not as much power as we want to make, so we're going to have to add some boost. So I like to think of this as, well, what percentage ratio, if you will, of increase am I going to need from the boost? We tend to look at power as a function of airflow. You've always heard an engine's an air pump. You never hear anybody say, you know, an engine's really a fuel pump. If I double the amount of fuel I put in there, it makes twice as much power. Nope, sorry, it doesn't work that way. But if you increase the airflow and you use enough fuel to burn the air, well, you're probably going to increase the power proportionally, right? So as a ratio, we look at something called BSAC. If you guys have been out there working on engines for a while, tuning carburetors, you've probably heard of BSFC, brake specific fuel consumption. It's an efficiency measurement of how much fuel you need per horsepower the engine's going to make. Well, this is the same measurement, except it's for airflow and it's based on mass units. So if I said airflow in mass units would be pounds of air per minute is the typical value that you would get off, say, a dyno or an ECU or an EFI system or something like that. Well, as a general rule of thumb, a healthy, well-designed engine is about a 10-to-1 ratio. So for every 1 pound per minute of airflow, you can make about 10 horsepower. So you could go backwards and say, well, that means if I was making 650 horsepower and divide that by 10, I've already got about 65 pounds per minute of airflow. But my goal isn't to make 650 horsepower. My goal is to make 1,000 horsepower. So therefore, 1,000 divided by 10 means I'm going to have a goal of 100 pounds per minute of airflow, right? So I'm going to take my calculator here. I'm going to put in my goal of 100 pounds per minute, okay? I'm going to divide that by what I've already got, which is going to be 65, because 650 horsepower divided by 10 BSAC means I need 65 pounds per minute of airflow, right? So what I get is 1.538, or about 1.54, let's say, and that would be the bar of absolute manifold pressure that I would have to have. So I would say I need about 1.5 bar. So the 1 bar there would be my atmospheric pressure. Then I need another little more than half a bar of boost. So I'm going to need probably somewhere in the neighborhood of 7 to 8 psi of boost. But remember, we're going to have some losses and some restrictions between the air filter going into my supercharger, coming out of the supercharger, and the drag and friction in the pipes, whether or not we have an intercooler, the throttle body, the intake manifold. So my guess is if you built me a good cylinder head, 9 to 10-to-1 compression ratio, properly cammed 388, and you gave me somewhere in the neighborhood of 10 pounds of boost, we could probably get awfully close to 1,000 horsepower. So when you're sitting back on how did they come up with these parts, where did they come up with these numbers, hopefully you can see that they came from a calculator and they didn't necessarily require you to have 50 years of experience that I can't get because I don't have any experience to go to work and get experience. You know what I mean? We've all been on that little merry-go-round before. So that's a way that we do it. Now some engines can be really more compression ratio will give you a big improvement over how much torque you can make per cubic inch of engine size, and some engines will be worse. Just like down here, some engines will make more than 10 horsepower for every 1 pound per minute of airflow, and some engines will make less. But a poor engine usually will make 9 horsepower for every 1 pound per minute, and a really amazing engine might make 11, so between 9 and 11 is 10. It's a good rule of thumb. So keep that in your pocket for easy math. Guy says, I want to make 1,000 horsepower. You need 1,000 divided by 10, you need 100 pounds per minute. Guy says, I want to make 1,500 horsepower? Well, then you need 150 pounds per minute of airflow. To figure out how much boost it takes to get the engine to make that, you need to know how much airflow would the engine have all by itself just to start with. Now, there's other ways I could have done this that we teach in our classes, looking at CFM and air density and volumetric efficiency, looking at thermal efficiency of the engine and fuel consumption and number of BTUs and all that sort of stuff. But in order to make this less complicated, a 10-to-1 rule of thumb is really easy for you to understand and keep in your pocket and use anytime you want. So let's try it. I want to make 500 horsepower. How much airflow do I need? Did you say 50 pounds per minute? Well, then you got it right. So practice that. Take a look at these numbers in your spare time and rehearse this a little bit until it becomes second nature. And I bet you'll find yourself carrying a calculator around all the time, just like I do. See ya.
Ben Strader and his whiteboard, brought to you by ProCharger. Like, a lot of information right there. What, Ben in front of the whiteboard? If
Ben's a wizard, right? I mean, the calculator's like, oh yeah, you know, here's square root of pi, blah, blah, blah. I mean, he's just so smart, yeah.
Well, I like being around smart people. If you like being around smart people, then you like it. If you're intimidated and afraid of smart people, then you probably didn't like it.
Well,
like
it's
going through
math,
the process.
Right? It's all about the math. Yeah, that's Ben's thing, always. EFI or building an engine, do the math. If you do the math up front, then you can pretty much have confidence of you're going to get what you expect to get. If you want to make 1,000 horsepower, you better do the math on the front side to make sure you can do 1,000 horsepower. And, you know, we probably ought to go ahead and let people know now that a few things we said in there we aren't going to be able to do.
Have been updated due to the reality of the world. What are they?
Well, so the first thing was the bore size. We wanted to do 4/125 for the reason we mentioned, having, you know, big boost. You want to have more material in the cylinder to be able to maintain that bore integrity. Well, this is 2021, and if you haven't heard, it's kind of hard to get parts these days. And lead times on things have been a little longer, so to do the 4/125 bore with the ring package, the compression we wanted, it was going to take a lot longer time to get pistons, so we were able to get pistons right away. The guys at Mala hooked us up with some really nice pistons that are 4/155 bore. So we had to go 30 over what we wanted in order to get pistons, and we're going to cover that in a later video with Ed where we mentioned what we went to on bore size. So that was one change up, so it's going to be a little bit bigger cubic inches. I mean, not a ton than what we said, so we didn't want to give up that bore thickness, but the reality was we can either get what we wanted and wait and not have an engine this year, or we can try to get and have an engine and maybe not be exactly what we want.
Well, an example of a real life compromise. Sometimes you have to make certain compromises, like do you want it now or do you want to wait? You didn't want to wait. We didn't want you to wait, and so you made a bit of a compromise. And we'll see how it all works. I think that'll be part of what's interesting about it.
Exactly. And hey, you know, we are having a round table tomorrow with several guys about this issue because, hey, we know 2021 parts supply has been an issue. It makes you make decisions, and we're going to talk about that in full depth with some real industry experts tomorrow. So at this point, though, hey, having been as part of the team is great. We're excited about what the engine's going to be able to do. I mean, that ProCharger, Joe, that ProCharger itself is bigger than one of my dad's go-kart motors.
Yes. Yes.
It's insane.
Well, it's something that has just fundamentally changed drag racing.
Oh, talk about it.
Fundamentally changed drag racing in that it is now the power adder of choice, the centrifugal supercharger, and cars are running quicker and faster than they ever have before, and you know, I absolutely love it. But hey, we're going to keep on going. Just mention to everybody out there watching on EnginePerformanceExpo.com and our friends on NHRA.tv, there will be an opportunity for a little Q&A throughout the day, and so if you have questions about any of these bits, jot them down, keep them ready. Later on, we'll do some Q&A with some of our experts, and you'll have an opportunity to ask and maybe have your question answered. Now, we're going to start talking about our next segment, which is very important, align boring versus align honing. What a day, what a day, what a day. Yeah, my brain is swollen. I've learned so much today. They told us, don't start cars. We are not going to listen.